All right, I want to add on to our last example for the notes that we had earlier today. All right, this one is going to involve a variable, and you do that a little bit different than you do a whole number like 18. Let's put a k to the 7th power. We want to simplify that radical. So we can go ahead and break it apart so they each have their own radical. The way you break down the 18 is going to be different with the way you need to think about breaking down a variable to a power. Okay, because finding a perfect square inside of a whole number is different than finding a perfect square inside of a variable raised to an exponent. What I need you to recall is when you are multiplying like bases together, remember that you add your powers together. So if we apply that to k to the 7th, think of the different ways we can turn k to the 7th into a product. If we're adding the exponents, that means we could have k to the 6th times k to the 1st, because if we add the 6 and the 1, we would get k to the 7th. We could break it down as k to the 5th times k to the 2nd, or we could break it down as k to the 4th times k to the 3rd. So I'm thinking of all the ways I can add two numbers to get a power of 7. So these are three possible ways that I could break down this particular radical. I need to find out which one contains a perfect square and which one has the largest perfect square. So let's think about what a perfect square is. A perfect square is when you're multiplying the exact same thing together to get your perfect square. All right, so let's just throw some examples out there. If I have k to the 10th power, and I want to break it down to two values that are exactly the same, remember, the rule is you add your powers, and I need the powers to be exactly the same. I can have k to the 5th times k to the 5th. That means the square root of k to the 10th is k to the 5th, because I'm multiplying it by itself to get k to the 10th. And remember, we're doing it by adding the powers. So thinking about powers is completely different than thinking about a whole number, a coefficient. If I were to take k to the 8th power, that is a perfect square because I can multiply the same thing together to get k to the 8th. Because if I do 4 plus 4, I will get k to the 8th. So what I'm trying to point out here is anytime you have an even exponent, you're going to take half of it to see what the square root will be, because that's what you're going to multiply by itself. Well, I have an odd exponent. So what you want to look for is how you can add two numbers so that one of them is even, because even numbers are the ones you can take half of. So I want to find the combination that has my largest even number. They all have evens, so any of these even numbers are considered perfect squares. I'm going to pick the one with the largest even number. So this is the combination I'm going to use to break down k to the 7th. So what you do is just take your exponent and decrease it by 1, and that's the combination you want to use. Just think, 1 plus what is going to get me this exponent? That's how you break it down. Let's break down that k first. If I do k to the 6th times k to the 1st, that is the same thing as k to the 7th. This is considered a perfect square because I've got to think what number plus itself, we're using this rule, can get me k to the 6th. That's how we're going to think about it. Let's go to our 18 and break it down. The largest perfect square you have at an 18 would be a 9 if you take 9 times 2. So this would go with the 18. This is for the k to the 7th. What you need to do is identify who the perfect squares are. This is a perfect square. This is a perfect square. So these two can be evaluated. These two here will stay under the radical sign. So if we take the square root of 9, that becomes a 3. So this is gone. Go to your next perfect square. To get k to the 6th, we're going to do k to the 3rd times k to the 3rd. That will get me k to the 6th because I add the 3 and the 3. And what you're trying to do is find the same number here as your exponent. So the square root of k to the 6th is k to the 3rd. As soon as you take the square root, you are out of the radical symbol. You do not have a square root symbol there anymore. So this is gone. It's turned into k to the 3rd. These two, you cannot do anything with them. So they both stay under the radical, but they can come together and be under one radical. And this would be how that final answer would look. Okay, so we'll call that example 4. So if you wanted practice breaking down another radical, I can do a quick problem here just with a radical. Let's say we want to simplify x to the 15th power. Okay, so what you need to do is break that x down. The biggest even number that you can use would be by decreasing this by 1 and making it a 14. If you take x to the 14th and multiply by x to the 1st power, if you multiply x to the 14th times x to the 1st, you would add 14 plus 1. That would get you x to the 15th. So this is a good way to break it down. You always want one of your powers to be even. Even exponents, those are the ones you can take the square root of. You are not thinking of it as normal square rooting. To get x to the 14th, to square root that or simplify it, you want to know, remember, we are using the addition rules. What two numbers can be added to get a 14, but they have to be the same two numbers. This is a perfect square because if you take x to the 7th times x to the 7th, it would become this. So this is the square root of this. He is now gone because we evaluated that. This is left. You can leave it as x or you can put the 1 there. So this would be your simplified form for that original problem.